Welcome to another Stat 420 video. In this video, we're going to talk about statistical power as well as post-hoc testing in relation to ANOVA using R as well. So I think we've talked a little bit about statistical power before. It's certainly in chapter 12 of the book if you've kind of seen that already. But it kind of starts with this idea of what are the different scenarios that could happen when I do a hypothesis test using a significance level and doing a kind of a reject or fail to reject decision. So again, like I kind of mentioned this first, that when we do a hypothesis test and we get a p-value, we can still interpret the p-value just as it is. We don't necessarily, depending on what we're doing, we don't necessarily need to be making like a reject or fail to reject decision, as much as the p-value is still giving us insight about what's going on and how confident we might be that some kind of effect exists or doesn't exist. However, if we are doing this kind of like binary choice, we're deciding to keep the predictor or not, we're deciding to use this in the model or not, then we're going to have this kind of binary decision. So there's kind of four scenarios that can happen here. The first is that the null hypothesis really is true and that we correctly fail to reject it, meaning that we're saying that it could be true, it is a true negative. However, we could also falsely reject the null hypothesis as well when it really is true, and that would be what's called a type 1 error. It would be a false positive. So it's kind of like we're setting off the alarm, but there's no fire. There is no difference, there is no effect, but we thought there might be, so we set the alarm off and said that there was. So this is called a type 1 error, and type 1 error is going to be the size of your significance level. So if I set alpha equal to 0.05, that means that I'm allowing a 5% chance of incorrectly rejecting the null hypothesis if it were true. So alpha represents your type 1 error when the null hypothesis is true. Now there's also the scenario where there really is some kind of effect going on. There is a linear relationship, there is a difference based on this grouping factor, and that would be the null hypothesis is false. So we could correctly reject the null hypothesis. That would be great. We have correctly rejected it. We have correctly stated that there is some kind of relationship or effect. But we might also fail to reject, and that would be what's called a type 2 error. So it means that there really is something going on. There really is a fire in the building, an emergency, whatever, but we didn't pull the lever. We didn't find enough evidence to come to that conclusion. And this is called a type 2 error. Now, this right here is important because this represents what's called the power of our statistical test. So power is our ability to correctly reject the null hypothesis and how often we will do that if it's the case. So there's a couple ways that we can improve our statistical power. Number one, we can have a larger sample size, because the larger our sample size, the better positioned we are to detect an effect if there exists. Because hypothesis testing depends on your sample size. The larger my sample size, the smaller my standard error, and therefore if there exists some kind of effect, I can kind of see through the sampling variability, I can kind of see through the noise and detect that effect more confidently when I have a large sample. Now, and this is not really something you really have a control over, but it's just kind of a reality that the bigger the effect size really is and the less statistical noise there really is, the easier it is to find that effect. So again, we can't manipulate the second part, but it's just a reality that if this is true, the easier it is to find it, the more power we would have. If we're doing an experiment, this is kind of a small consideration, but assigning our units equally to each group would improve our statistical power. So for example, since we're talking about ANOVA, if we assign 150 people equally to three groups, 50, 50, 50, that would give us a little bit more power than doing something like 30, 30, 90. So again, if we're doing observational studies, this doesn't matter, but in experiments, assigning people equally to the different groups does give us more power. And I put this down here because you don't necessarily want to do this, it depends, but obviously a higher significance level means that you have more power. So if you're okay setting your alpha to 10%, and having a type 1 error of 10%, then it's really easy to reject the null hypothesis. But obviously, you're increasing your type 1 error, so you shouldn't necessarily do this. You should probably keep it pretty low because you want to be confident. You don't want to falsely accept it either. So so you want to keep it as low as reasonable, I would say. So the reason we're talking about this is in part because we're going to talk about post hoc testing. So after we complete an ANOVA, we have to decide what's really going on. Because if you remember, in ANOVA, our null hypothesis is just that all the means are equal. So if we reject that null hypothesis, all we're saying is that at least one of the means is different. Maybe more, but at least one of them is different. But the ANOVA itself isn't necessarily telling us which means are different from which means. So that's where pairwise testing kind of comes in. And there's really three general choices that we have when we do this. Number one, we could do multiple pairwise t-tests with no corrections, but that's not a very good idea because we are, as we'll see in just a second, really increasing our type 1 error if we just do more hypothesis tests and keep our alpha level at, whatever, 0.05 or 0.01 or something. Well, now there's a lot more chance to incorrectly reject the null hypothesis because we've just done so many tests, and as we know from p-values, they're uniformly distributed from 0 to 1 if the null is true, and we might risk getting below our threshold by random chance if we keep doing t-tests. So a second option then is to do multiple pairwise t-tests but with corrections. So the Bonferroni, I think I spelled that right, the Bonferroni correction would be one option where you could either kind of like deflate your significance level or you could inflate the p-values that you're producing. But either way, you're just kind of adjusting the p-value according to how many groups you're comparing. And then the third is to do a test that's specifically designed to pool your variance across all groups. So instead of just looking at the two groups that you're comparing in the pairwise test, you kind of make some pooled variance measure and use that in all of your pairwise testing. And that would be a Tukey on a significance difference test would be the most common method there. So I typically prefer the third, the Tukey test, because I think it's just the most straightforward to interpret. I don't like necessarily using a Bonferroni correction because I think they can be very confusing to readers. So I just say that a Tukey test is accounting for all the information at once. And to me, it just seems a lot more sensible to use and a lot more sensible for a reader. So just kind of a word about this, why don't we do the t-test without corrections, what's going on? So it's because of issues like this where this is kind of a silly comic, but this idea that, let's see if there's a link between jelly beans and acne, but wait, what if it's only a specific color of jelly bean that causes acne? So I go through and I test 20 different colors, and 19 out of 20 times I get a p-value above 0.05. One time I get a p-value below 0.05. Well, now we have news that green jelly beans are linked to acne. So this is why, that's why this is probably not a good idea in general, is because for every pairwise comparison we're doing, that's another test and another way to accidentally get below a value like 0.05. So that's why we need to adjust or use a different method that's pulling our information together. So we'll do this pretty quickly here. There's not a whole lot to do here. But I'm going to start by simulating 4 samples with the same mean in this case, and just putting them in a data frame. And then we can do what's called a Tukey test, and it looks something like this. So what I'm going to do is every pairwise comparison will show up over here. It's going to report the actual difference that we observe between the sample means. It's going to produce a confidence interval, a 95% confidence interval for what that true difference really is, and a p-value that is adjusted according to this kind of grouping method, this shared variance that the Tukey test is going to do. So this is going to be higher than what you'd get if I just did a 2-sample t-test of groups B and A. So it's pooling all the information and keeping that in mind. So in this case, it looks like I don't have any noticeable differences, but again, if I do it again, I might get a little bit more difference by random chance, like here. It's a little bit lower, but not that much lower. And now compare that to a pairwise set of t-tests where I don't have any adjustment on the same data, by the way. First of all, the information comes out a little bit differently. They do it in a table, but you'll notice that these p-values are a lot smaller because I'm not doing any adjustment. I'm not pulling my information. I'm just doing t-tests, and I'm going to get some low p-values by random chance every time I do this. So you can do a Tukey test. You can do a pairwise t-test with an adjustment, but either way, that would be kind of the way to go here.